So I have the great honor to introduce this year's Noether lecturer, Shafi Goldwasser, who's going to tell us about establishing trust in machine learning.
Okay, thank you very much. And I'm very glad to be here. Thanks for the invitation. So I spoke here actually 4 years ago. In fact, we just were trying to figure out when it was. I think it was 4 years ago. And my title at that time was Addressing the Growing Distrust in Algorithms. In particular, it was really machine learning algorithms. And at the time, the worry was just that a lot of the courts were talking about, instead of having bail that's based on cash, they were going to use essentially neural nets to establish whether people should go out on bail or not. And some states were talking about adopting it. And that was the big discussion, and it shouldn't be done because it wasn't explainable and you couldn't really argue why the software was saying yes or no to let people out on bail. But since then, a lot of things have happened, as we know. I mean, COVID is not here, there's a lot of other plagues. But in some sense, AI has been an amazing revolution, and that's a little bit tongue-in-cheek, but I don't know if you've seen this Peter Sellers movie. Everybody? Somebody? Okay. How I Learned to Stop Worrying and Love the Bomb. So really, this machine learning, there's no other word to say, but it is a revolution. For those who believed AI, those who didn't believe AI, I think it's hard to argue with that. It started with deep learning, and now all the rave is large language models. Actually, now people are talking about new models. We're talking about questions like how do you even distinguish between human and machine intelligence, but not theoretically, as in the Turing paper, but really actually when people are submitting homework assignments and solving problems on using large language models. I'm actually involved in a project called SETI, which is all about trying to translate whale communication. So there's some promise that we can use these large language models to translate actually non-human communications, whether you call it language or not language. And these days, there are many people, at least, especially the ones working in AI companies, that are saying that soon we will surpass human intelligence. And there are betting markets about when is that going to happen in different disciplines. And the problem is that all of this is done without really understanding full well why does it work so well. And then the second question is, should we really trust models that seem to perform very well on benchmarks and, as far as we can tell, on human kind of defined tasks, but when we don't understand it? But this is sort of a nice philosophical question. The truth is that sort of the genie's out of the box, and it's already being used. It's being used in health, and it could be used for control of prediction of disease, spread of disease through network modeling, for drug discovery. Everybody's talking about these new proteins that you can discover for traffic patterns. Speech recognition, we're all using it. For policing, for financial markets. And so it's already being used. And yet there is this issue that we have to recognize that really, instead of whoever was the experts before, now the expertise, or the power more so, lies in the hand of those who have access to a lot of data and a lot of algorithmic knowledge. And there's a power shift here. And since I'm in IAS, I think that maybe should be very interesting to this crowd is really, what does this mean for mathematics, okay? So there's a huge promise for applications of the kind that I mentioned, health, traffic, policing, and so forth. But more and more people are talking about the use of these machine learning models, generative machine learning models, not just the kind that say yes or no and classify, for helping mathematicians. There was a workshop just now, last week, at the Simons Institute at Berkeley, joined with what used to be called MSRI, and now it's called SL Math. And the topic was AI for mathematics and theoretical computer science. It was actually fascinating. Lots of new work. And if you think about this as a machine learning problem, where you have you want to build a sort of a large language model that helps mathematician, what is the data? That was one thing that was discussed quite extensively. The data is access to old theorems, old proofs, old techniques. So in the same way that when they talk about large language models, they talk about reading the entire Wikipedia. Here you need access to old mathematics. Old might be yesterday, but the one that's already we have access to. And the trust question, which is the topic of my talk, which was a bit vague when I talk about it in general, should we trust these models which we don't understand to make decisions about traffic and health? In the realm of mathematics, at least it's well defined. That is, can we verify this artificial mathematics or artificial mathematical intelligence? This is a phrase that I heard during the workshop, and I love that word, artificial mathematical intelligence. But in any case, can we trust, for example, the theorems where they be proved by an AI model? Proved, generated, and so forth. And at least mathematically speaking, we have some notion of a proof. And what we mean by trusting is whether it satisfies a proof or not. And one of the things that I'll talk about today is, can this really be done? Can you come up with models that not only give you suggested, mathematical hypotheses, or maybe they claim to prove something you suggested, but that also are able to, somehow can we verify these proofs? Okay, so that's going to be part of the topic that we're going to tackle. But that's going to be sort of midway through the talk. For now, I want to say that I'm a cryptographer in training, even though I've worked on complexity theory and algorithms, but really sort of my viewpoint is always cryptographic. And from this point of view, what does cryptography have to do with the question of the previous slide and machine learning and trust and all that? So often people think of cryptography as a bunch of tools. You can encrypt, you can do digital signatures, you can maybe do things like zero knowledge proofs, deniable. There's lots and lots of primitives that people come up with, which are very cool. And what's the unifying theme? First of all, there's the same group of people that work on these problems usually, but that's not a unifying theme really that you can put your hands on. But the unifying theme is that cryptography, it's not necessary, there's no need for it, except when you think that there's some adversary lurking. So two people can communicate over the phone, and maybe you want cryptography because you think somebody's listening in and you want to make sure that the communication is secret. Or if you're signing to a bank and you don't think anybody's going to try to pretend to be you and withdraw your funds, everything's okay. But if you think that an adversary is there trying to identify themselves as you, then you need some kind of cryptographic protocol. So in other words, all of these primitives, essentially what they do is that they enable us essentially to trust technology, even when the adversaries are present. So we've got some technology and we'd like to pretend that there's no enemies. And the crypto, when it's done well, essentially allows us to do so. And it's so much so that there's a recipe really. And the recipe, somehow, a lot of slides here seem to have been skipped, but the recipe usually is you define a cryptographic task, okay? And that could be secret, privacy, authentication, whatever. Then you define what it means to be secure, okay? And that could be weak secure, high secure, but you define your mathematical notion of security. Then you propose a solution. And the important thing is then you're supposed to prove it. So you're supposed to prove that the solution you design is secure according to your definition, okay? And often in cryptography, which you probably know because of Avi, we make assumptions. So under an assumption, we make a proof of that sort. The assumptions are many kinds. The best assumption that we usually like is that the sum problem is computationally hard. People have talked about factoring integers, finding short vectors in a lattice. And the reason why this is attractive to us is because it's sort of a win-win type of result. Namely, either the assumption is true, and then you have a secure cryptographic system, or the cryptographic system is insecure and somebody broke it, and in turn what you get is a fast algorithm for a problem that you thought was hard. So either way, whether you break the system or not break the system, you're a winner. If you don't break the system, we have security. If you break the system, you solve a mathematical problem. So at least we feel we didn't waste our time. Okay, so the proposal then is that we use the same recipe for machine learning. So in other words, now the tasks are not encryption, like secrecy, authentication, and so forth. There might be some machine learning tasks, and we'll talk about examples. Machine learning tasks could be proving mathematical theorems. It could be, coming up with a system for IRS to assess whether your tax returns, I know, at least I am worried that I'm not going to press the button tomorrow, but maybe there'll be an automatic system for IRS to evaluate whether your tax returns are correct. It could be lots of tasks, and you could have different definition of what it means that you've done it successfully, but we want to follow this recipe. And we want at the end that there'll be an assumption, and then a proof of this implication. Computational hardness is not the only assumption. Sometimes what you do is you say, well, there's not just a single entity that you are suspecting, say maybe is adversarial. You'll have many entities, okay, distributed the power to perform some function to many, and you don't believe that they all collude against you, but maybe you believe that less than 50% collude against you. So that's not everybody colludes. Sometimes they're physical assumptions. Sometimes, like you're saying, that maybe they're so far apart that the speed of light, somehow they cannot communicate, and therefore it's going to be secure. And sometimes there's trusted hardware assumptions, and I'll talk about that in a minute. Just so when you leave this lecture, you know everything there is to know about cryptography today. Okay. By the way, sometimes we don't show that something is possible. We might show something is impossible. Also that under an assumption, saying, you know, it is possible that the adversary can cause such damage that cannot be prevented. In which case, either your definition of security is too strong and you should modify it, or you should not attempt to achieve this task of machine learning. Any questions? No. Okay, good. There's not that many of us, you can ask questions. I'm happy to answer in real time. Now, one thing one can say about this idea, this recipe, is that whereas cryptography really was designed with the idea of an adversary, because otherwise there's no need for it, machine learning has a lot of utility without thinking adversarially. After all, these machine learning, we might assume that they don't want to destroy our lives and destroy the world. Still, I think everybody recognizes that they're such attractive targets. There's so much power in these AI systems that you might as well assume that there's an adversary who's a worst case adversary. Don't assume a particular behavior, that it's benign, that it has limited power. You want to say they're worst case. You might assume, we do assume, there's some computational limits on it, so it doesn't work, it doesn't have exponential time to its disposal. It has what we call polynomial time. But it's worst case strategy in polynomial time. Okay. And now from here on to the rest of the talk, really, I wanted to give you a bunch of examples, okay, of what would be possible adversaries in this machine learning pipeline, which usually consists of you collecting data, then you're training some model, and then you hopefully audit the model. So there's a stage after the model has been designed, you audit it, and finally you use it in the future. Who are the adversaries? What is this, paranoia? So I will hopefully convince you that it's important to think about adversaries. And the kind of algorithms that I'll talk, there's what we call usually a training algorithm. So that sort of the schematic is there's data, this is X, and there's Y, which is the label of the data. You can think of this as an application for school, and Y is got accepted, didn't get accepted. Or it could be a bank application for mortgage, and Y is I gave it, I didn't give it, and so forth. And then there's a training algorithm. It takes all this data, somehow summarizes some very important insights, and produces now a new algorithm, which I'll call H, which is a model, okay, and hypothesis, if you like. This is what H is for. And the goal is usually to minimize some sort of error between of this H. So for example, that minimizes the probability that H of X is wrong. So given a new X, it doesn't predict Y. Sometimes you have a more complicated loss function. You want to estimate the expected loss for the between what H says on X and between the true label Y. And on the other hand, we're going to have here, and various results in the talk, we'll talk about different right-hand sides. Sometimes these are the H's. Sometimes the H's are just classifiers. Like you give it, like say, information, then it says yes, no, accept, reject. And sometimes there's like large language models like ChatGPT or something, so they generate sequences, or they maybe even generate probability distribution over sequences. Okay, so that's what I'll be talking about. There's a training algorithm, and then there's an H. Hi. All right. So what are the sample goals, the tasks that we want, that we worry that adversaries are going to stand in the way? One is going to be privacy. Second is going to be verification. Third is going to be robustness. And today, most of the day, I will talk about the first two, whereas tomorrow in my second talk, I will talk about the third. So what are these? But I want to say what they are. Privacy is, since we already said, I said it already 3 times, the power of machine learning comes from data. The data might be data of individuals, not in the case of mathematical proving, but in the case of many other cases. So it might be my private data that I don't want people to be trained on. So the question is, how do you keep the privacy of my data and still achieve all of machine learning as as we know it and as we probably will continue to know it. Second is verification. So let's say somebody trained the model. How do you verify, since this model was possibly trained by someone else who might have some other motives except for your best interest? How do you verify that it has the properties that they claim to have? And maybe there's bias there, maybe the answer is incorrect, and so forth. And the third thing is robustness, or what I sometimes call resilience. And that is, okay, there is a model out there. It's been trained on some past data. Maybe you've even verified the properties that it claims, and now new data comes along. One of the examples that people often use is that COVID, when I was here, actually, 21, I was still kind of coming out of COVID, that a lot of the lungs of people, images that had COVID, didn't have COVID, look somewhat different. And maybe your algorithm was trained on, old lung images, and now to predict whether you have, God forbid, a tumor or something, it doesn't really match the new images. Or any disease, doesn't have to be COVID. So we want our algorithm to be robust for distribution shifts or for maybe other, even more adversarially chosen inputs. So those are three things. There are more things. These days, and I will mention about that tomorrow, these days when people talk about large language models, there's a word that keeps on coming up, which is safety. What about these algorithms? Maybe they're not safe in many ways. It's not clear what people mean about safety. So for example, I celebrated Passover, and we made this Passover Haggadah a few days ago, and we gave a picture, all kinds of pictures of our family in the past, and one of them was my parents and me on the beach in Tel Aviv in bathing suits, okay? It was like, I think, 8 full bathing suits. So ChatGPT dressed us all. And apparently that's a thing because there is some kind of policy which is, it's not safe because maybe, somebody is doing pornography, or the other kind of safety is maybe somebody's asking how to attack a plane or many other things, okay? And safety is a big word. So who's the adversary there? The adversary there might be the people who are submitting requests. And you want to somehow address that. So can you do it? Can you not do it? How much power do you need to do it? That's another question you could ask. All right, so let's start with privacy. So the truth is that privacy is the easiest thing to address. And possibly I even mentioned it in my talk from 3 years ago, because we have lots and lots of methods. So cryptography really, from 1976, roughly, they've developed tons of tools. And among them, there are things called secret sharing. So you can take a piece of information and build it. Usually, you'll do it by interpolating a polynomial that goes through the shares. And if you can reconstruct the polynomial, you know what the secret was. And each party, so each party has a share, which is a point on the polynomial. There's something called multi-party computation. There's garbled circuits, many things, okay? And all of these tools actually are relevant to this problem of machine learning training privately on data, by privately meaning that you cannot actually look at the data and yet you can take advantage of it. So in particular, here's what it looks like. So it looks like this. The training data, this is the simplest form. Training data comes in, but now it comes in encrypted. So there's some encryption scheme, and I'm going to need a special one. And when somebody submits their data, whether it's a hospital or an individual, they encrypt all their data, okay? And now what you want to do is to be able to run the training algorithm that before was looking at X and Y, but now only has an encryption of X and Y. Now, intuitively, the encryption is useless because that's the point. We don't want to be able to tell what X and Y were. And yet we would like to be able to compute and get at the end an encryption of the hypothesis, encryption of the model. So if we want to think about model as some big neural net or transformer, they have these parameters. You probably have all heard these words, and you probably know more than me exactly how it works. In any case, let's say that we had an encryption algorithm that could give you this. And in fact, these are called homomorphic encryption algorithms. And the property of these encryption algorithms is not only that you can encrypt and decrypt, but you can actually go from X. Let's say X is the information that we're trying to hide. And you encrypt it by running some encryption algorithm, getting C for ciphertext. And now there's also something new, which is for given a function f that you'd like to compute on X, okay, there's a way to run an algorithm called eval of f, so that at the end, it takes the encryption of X to the encryption of what? Of f of X. And namely that from C prime, you can go back through a decryption algorithm to f of x. So in other words, this is a schematic that tells you not only that I can encrypt and decrypt, but I can actually, under the hood, under the encryption, do a lot of evaluation functions, f of x, f of x, g of x, and so forth. All the time, everything remains encrypted. But at the end, I can decrypt and get back what I've computed over x. Okay, so that's what it's called homomorphic encryption, because usually it's based on mathematics that has a lot of homomorphic properties. And we have such a thing. Why is it useful for us? Because think about it, if I could do that, I could run the entire training algorithm under encryption. And at the end, I would get an encryption of the training algorithm. But now I want to actually be able to use the training algorithm. So at this point, somebody has to decrypt this encryption of H. And that somebody, now I'm going to give, essentially, we think of this as a cryptographic key. It's shared, it's broken into pieces. The shares are given to different entities, and each one applies its piece so that at the end you can find it, get H. So what are the assumptions that we've made here? I said that there are assumptions, but there's no free lunch here. One is that we have such an encryption function, and that is based on some mathematical problem I'll define in a minute. Some of you may know it. It's called learning with errors. It's a problem that we don't know how to solve quickly. And under the assumption that there is no algorithm to solve quickly, this is a secure encryption function. So in your mind, you can think about it as like people usually talk about factoring is hard. But for getting homomorphic encryption with these extra properties, we need a different assumption. Factoring is hard is not enough. And the second assumption is that these guys do not collude. Because if they colluded, they could reconstruct the key, and they could essentially figure out also how to decrypt the encryptions of X. Okay, so this is sort of a blueprint, but it's exactly what one does. Yes, you're doing like this? No? No. Okay. What is this learning with error? Learning with error is the following problem. You're given, let's S, we think of it as a secret vector in ZQN, so over some field ZQ, a vector of length n. And now the problem is that there are the secret S, we think of it as S1 through Sn, these elements in ZQ. We are given also equations in these variables. Let's say n here is 4. I'm given equations, but if I was just given, what does it mean given equation? I'm given the coefficients and the solution on the side. Of course, you could do just Gaussian elimination. So there are two differences here from standard linear algebra. One is that these are modular equations, okay? And so that there's some truncation. And second is that I'm actually not giving you the right-hand side. There's an approximate sign. I put some noise, some Gaussian noise on the right-hand side. So 8 is really the correct answer plus some noise. 16 is the correct answer plus some noise. So I'm giving you a bunch of noisy modular equations. It turns out, and so it's like a truncation on the lower half, and the noise is on the top half. Turns out this is a hard problem. First of all, it's hard because we don't know how to solve it. But more than that, it's been shown, there are proofs showing that it's hard as decoding random linear codes. It's as hard as approximating the size of the shortest vector in worst case n-dimensional integer lattice. This is work by Aitai and Regev and Machiancho. So there's a lot of work that has been put into showing the hardness of this problem is. What does it mean? As hard as? The usual thing. If we can break this, if we can actually do better than distinguish these equations from truly random equation where there is no solution S, vector S that satisfies these equations, okay, then it can be turned into an algorithm that solves these problems. Okay? So this is the hard problem that our crypto systems are based on. And in fact, they are also hard for quantum computers as far as we know. Again, tomorrow somebody may come up with a quantum algorithm. Someone can come up with a classical algorithm. But as I told you, it's a win-win. The best known quantum algorithm even runs in 2 to the n. And the National Institute of Standards now, in fact, because they're supposedly preparing for post-quantum era, where people are going to have, let's say, quantum computers, they want things which maybe break the classical systems, like the factoring-based system, but don't break the new system, which would be based on these problems. Okay, so, and there's open source and all of that. What's the problem then? Everything's good, we go home, privacy is done. So the problem is that is very large scale data that we're talking about in order to train large language models. And these methods are not fast, okay? So it could be nice in theory, but you need a lot more theory in order to make them, useful. So there are a few So what people did is, over the years, starting in around 2020, is that they applied it in several domains and were able to get good results, okay? And I just want to flash a few of these type of applications. So most of the applications have been in sort of the bio and health domain. So it started with genome-wide association study, mostly because this is an area where, one, you need a lot of data to get signal. So just doing a little bit of data is not meaningful. And two, we know from genomic sequences that actually privacy matters. So if somebody has access to my sequence, they don't know my name, but they have the sequence of my son, and they do know their name, they can associate back to me. So it's a place where both scale is important, because you need to work with a lot of data, and privacy is important. And the GWAS was the first example. So here's a method in a paper that I'm part of, where we did the genome-wide association study, and extrapolation was like 100,000 individuals, 500,000 SNPs, these parts of the DNA in 5 hours on a single server. So real-time response is not necessary anyway. But this is 2020. By now, it's much faster. Now, what this does is that it takes a lot of genomic sequences, okay, and does this and tries to find signal connection between phenotypes like illness and particular alleles. But the advantage here is this genome sequence. Nobody has enough genome sequence, but there might be Broad Institute in Boston and UCSF in San Francisco and other places. Together, there's enough data. And the advantage of that they're not all in one place, is that the key, you can think of these providers like the Broad Institute, UCSF, I don't know, other hospitals and so forth. Each one of them has a key piece, and only when they join their forces together will they be able to figure out the results of the GWAS study, and they are not going to collaborate in order to find individuals' data. And then in 2023, there was another piece of work that I was involved in. And there, the idea was, let's go to a real hospital. Because usually this GWAS, there's some data that you're given, it's not necessarily real data. It's data to test your methods. So this was an oncological study in a hospital in Israel, in Ichilov, where there was an analysis of oncological data. And what was interesting about that is also that it's not just everybody has the same type of data, but it might be that you are working with the hospital, and then you have also the pharmacies, and you have data of different types. So you have the same person, but they have gone to a lab, or they've gone to get their genome sequence and so forth. So we want to do a joint operation under encryption. It's a harder operation, and this can be done now. In fact, there's a whole library of things that can be done, all kinds of statistical operations on the underlying data. And all of this is not just by having more computers and more GPUs, but it's actually by having sort of algorithmic breakthroughs, by doing something like packing more data in a single encryption, doing more clever bootstrapping, for those of you who know a little bit about encryption. But the fact is that this can be used to do this kind of statistical analysis on data without ever decrypting it, without ever looking at data in the clear. The last thing is, I said that we need all kinds of assumptions. I said computational hardness, like learning with errors is hard. I said about the key holders not collaborating with each other, but I also mentioned trusted hardware. Why? Who wants to trust hardware? And the reason is, again, because if we want to do things like, if we think about the computations we do, some of them are just linear computations. Some of them are like logistic regression. Some of them already deal with neural nets with lots of levels. Some of them large language models. The scale is humongous. And it seems that at this point, we need something to speed it up. So what people have done here is they said, if we look at the computation versus the assumption, then it possibly is that we need to add to these two other assumptions that I had before, also some trust in hardware. So what's a trusted hardware? A trusted hardware is sort of the new kid on the block, even though it's not that new. And there's something by NVIDIA, which is called H100 GPU. The issue is, it's like you can think of it as a box where encryption data comes in. Inside, there's a key that decrypts it, does an operation, and encrypts the result. So rather than doing it all by an algorithm that works with encrypted data, some of the operations are done in a box where the assumption is nobody can open the box and look at the key. The thing is that, and there used to be some Intel secure hardware. The problem is that secure hardware, that's yet another can of worms. There's something called side channel attacks. It's possible that if two people use the same piece of hardware, secure hardware, some remnants of the previous computation are in the memory there. I mean, I don't understand much about this, but I think it's actually fascinating that people are able to take things that are called secure hardware and completely recover the key, not for the top guy, but for this lower guy. But it is an assumption that is made, and people are building, actually we have some work on it, building protocols. There's something called federated learning where you also do encryption, but you also assume that you have some trusted hardware in your disposal. Okay, that's all I want to say about privacy. Okay, that's it. So I'm saying privacy, sort of, we have a handle on it. We have to get better, faster encryption scheme, maybe more secure hardware. Maybe we can come up with another assumption on the scene, but it's not a problem that requires kind of a total shift of mind for someone who's an expert in cryptography. So verification is a much more interesting problem from that point of view. Any question on the privacy? Yeah.
Can I think of this type of privacy as being a different regime than, say, differential privacy?
Okay, great. I should have said something. So, no, but I'll explain why. So the way I said it, the data is exact. I didn't add any noise, nothing. And at the end, the model is a model that you train on exact data. So that means, and what differential privacy is all about, say, well, but it could be that that model by itself spits out my Shafi's name in her medical records. That's not good. So there are methods, differential privacy methods that some are more efficient, some are less efficient, but the idea is that you put noise, so the model that comes out, this H is going to H star, and H star is guaranteed to not reveal, so essentially whether I was in the original, I gave my data, my XY, or didn't, the H star should be the same. Now, these methods can apply. That just means that it's a different H. So it's a different training algorithm. It's a training algorithm that adds noise. So on top of that, you've encrypted all the inputs. Now you run the differentially private training algorithm, and you get the new H star, encryption of H star. So in a sense, a training algorithm covers also the DP algorithms, okay? Actually, the differential privacy raises an interesting security problem, and that is who's generating the randomness? Where is this randomness coming from? Is it good randomness? Is it private randomness? We've shoved that under the rug, the other works that deal with that. But okay, good question. Okay, verification. So, new picture. So I want to think about machine learning as a service. If you live in San Francisco, I'm actually kind of amazed every time I come to the East Coast. The billboards on the way from Berkeley to San Francisco, or in the whole Bay Area, it's all about AI. Okay, here, not so. So in any case, this is a company called Hive, and that's their logo. It's one of the things you see when you drive from Berkeley to San Francisco. And the way I want to think about it is that there's a client, might be a doctor, might be a bank, might be I don't know who, and they have data, and they give the data to a service provider who builds a model for them. After all, we don't know how to do it. We want to give it to someone else and then have somebody give me back a model that's suited for my application, okay? Now, why does this service provider have horns, these red in a tail? Because it's a service provider. I don't know I cannot trust them. So I think of them as possibly adversarial. And yes, just it could be that they had collected the data, or it could be that I gave them my data. And Hive specifically had a sign on the billboard saying, "We make AI work, don't just trust us, test us." So they also recognize that there's no reason to trust them blindly. Okay, but what does that mean really? Okay, so what kind of properties in particular might we want to verify from such an algorithm? So we can, the obvious first thing is to talk about accuracy. So what do we mean by accuracy? We'll talk about it in a minute, but usually accuracy would be, like the claim is 99% of the time we do a good job. Okay, then you could talk about correctness. Correctness is every single input, we do a good job. Do a good job means give it the correct answer. So in mathematics, it's obvious. If it's a theorem, the proof is correct. If it's a calculation, the calculation is correct. If it's something like a legal document, are you consistent with the tax law? Maybe that's also easy to define. There are other areas where correctness is harder to define. But I'm sure that all of you have had the experience playing with these large language models, and sometimes you ask them, give the CV of, the last one I did, I went to a opera in New York City, and afterwards I was looking for something about Pavarotti, and comes up, the first thing that comes up, so it's a history of Pavarotti, and they say it's a famous Italian director. No, not director, actually opera singer. So and this is trivial, okay? So there's a lot of mistakes. Okay, so correctness would be that such a mistake will not happen. Okay, you can talk about robustness, fairness, safety. There are lots of properties that you might want to be able to verify from this model. And in the future, supposedly there are going to be some laws, and you want to verify that it's consistent with the laws. Of course, if you could retrain yourself, but that's expensive. So you want to be able to verify cheaply using less time, less data samples, less memory, and maybe just having black box access to this model that was provided to you without looking inside. So that's the question. Can we mathematically do that? Can we verify? So let's talk first about accuracy. So we have a model designer, but now we're going to start thinking about this model designer as not just a designer, but it's also what I call a prover. So people have seen interactive proofs here, possibly, and he's going to be, and there'll be a verifier. The verifier is the client. The prover is Hive, or a machine learning company that comes up with models. Okay, and the model is this picture. So in practice, how do you verify the accuracy? You test against a bunch of benchmarks. Benchmarks are a bit problematic because everybody knows the benchmark, including whoever designed the model. So we have this paper with Amir Yudayov, Guy Rothblum, and Jonathan Schaefer, who was a student of mine, and now he's a postdoc, and I think he's going on for faculty position next year, which we call interactive proofs for verifying machine learning. So what do we mean by that? So Les Valiant in 1986 gave a definition of something called PAC learning, probabilistically and approximately correct learning. And his definition was this: you're given these XY pairs, and you would like to come up with the H, such that H minimizes the error, the difference between H of X and Y, with high probability. So it's probabilistically approximately correct. What we'd like to do is to talk about PAC verification. So probabilistically and approximately verifiable. Okay, and how would you define that? So this would be the definition. That's the definition we propose, and that is, you're saying that a hypothesis class, what's a hypothesis class? Now, it's not a single little H, but a big H. So it could be neural nets, it could be decision trees, it could be lots of types of machine learning algorithms, could be LLMs. We want to say that they're PAC verifiable if the following is true. There is a way the prover and the verifier can talk back and forth, okay, so they can interact. Verifier can ask questions, prover gives an answer, and so forth. Answers that he knows because he's trained the model himself. Such that there are three things should be true. Completeness, and that is that the probability that the verifier will accept H and the loss of this H compared to the best H is small. So in other words, we want to verify that the little H that I was given is within additive error of the best possible. It could be that the best possible is terrible, but I want to know that what I was given is not too far from best possible. That's what I mean by completeness. So if in fact the model is within additive of the best, I will accept. And soundness may be the more interesting one, and that is regardless of what the model provider does, how much they're trying to cheat me because they are adversarial, the probability that I will accept when the loss of the model is far away from the best loss is small. So in other words, I want to accept good models, I want to reject bad models. And good and bad are defined in terms of accuracy with respect to the best possible. And furthermore, finally, I want the verifier to be more efficient than the prover, either in time or number of samples or the quality of the sample. The definition clear? So basically, is it possible, for example, to verify much faster than to train and with less data? And the answer is that sometimes. So here's one example, and that is if we look at the class of models, is going to be look at Boolean functions where, if going from 0, 1 to the reals, whose Fourier coefficients, whose Fourier representation is not large. So in other words, it has only, it's sparse. Maybe it has only one non-zero coefficient, or maybe it has lots of non-zero coefficients, but only a few of them, T of them in this slide, are of significant weight. weird thing to choose, but it turns out this is a class that represents decision tree, low AC0 circuits. These are shallow circuits. So it's an important class. And what we can show that indeed this class can be verified. So I'm a prover. I train the model, okay? And now I'm showing it to the verifier and I say, hey, this is a really good one. You can verify this is as good as possible, this time more cheaply in the following sense. In order to train such a model, it turns out that you need to do what's called membership queries. You need to be able to ask from the X from whoever's giving you the data and get back Y for a bunch of polynomial number of questions. To verify, you just need to get a bunch of random samples. You don't need to do these membership queries. So you get X and Ys, which are labeled, rather than you choose X and get the Y, which is much harder, considered to be much harder. And the best, and this is actually, there was a result in 21 that we had, but it's been improved very recently by Gurinal, and they now can need access to a number of samples, which is not a function of n, but it's a function of how many non-zero Fourier coefficients are there, and these AR parameters, where epsilon is the difference between a h of x and the true y, and delta is the probability of correctness, so it's 1 minus delta. And they call it on the power of interactive proofs for learning. So again, what they're doing here, and what we did in the original definition, in the original paper, is verify that the model you're given is accurate, is as accurate as possible, plus minus epsilon. Okay? All right. Still, okay, now comes the more interesting part, as far as I'm concerned, because it's also newer, it's just from last year. After you've done, let's say you've done all this, it just gives you an average case guarantee. It tells you that this model that you have, let's say now let's switch to large language models. There's a large language model, and I've tested it on benchmarks, or I did an interactive proof, and it turns out that on a particular task, it's 99% correct. That's considered fabulous, okay? Maybe even 99.9 for task T. But then I have a particular input X, like Pavarotti, or more important, my lung scan, or MRI image, and now they have to decide to take action based on it. On my X, there's no guarantee whatsoever. It could be 99% correct on some distribution, but I'm not, on me, I have no guarantees. So the setup now is this. The X, think of it as a prompt, okay, to LLM. And Y is the answer. So there could be lots of possible correct answers, okay? But I want to know that the one I got is also correct. So how do you trust it? So whereas the model, this H should be little h, really. The hypothesis, okay, model, on input X gives a Y. What we would like from now on, and again, X could be a theorem. That's what you care about. Could be a calculation, could be a text query. And what I'd like now is to have possibility to not only get the output Y, but also get a proof that Y is the correct answer for X. So we need to define what correct means. And more than that, we need to define what is an acceptable proof. Okay, this is this paper with Noga and All and Guy Rothbluth. And we call it models that prove their own answers. And this sits in the context of, later I'll talk about Lean and Coq and a lot of math proving software out there, because this is a generalization of it. Okay, so are we together? What do I want to do? I want, on a particular X, when I get the answer Y, I want to have a proof that Y is correct. So what is a proof? What does a proof mean? Well, the meaning could be different when you're talking about a text query versus a theorem or calculation. So let's restrict ourselves to domains like a theorem or calculation where the notion of correct is well established. So there's a relation. So if we go here, there's some relation between X and Y, which is true. That's what I mean by correct Y, where R of XY is 1. So like a correct theorem, or if I add two numbers, the answer is correct, But it could be there are lots, if it's a graph and I'm talking about 3 coloring, there could be lots of 3 coloring. So it's not necessarily unique Y, but given a Y and an X, it's either correct or incorrect. So the way I want to define a proof here is the following. There is the model, as we said, and there is an input X, and it gives me a Y. What I want now is to say that the correctness is defined with respect to a verification algorithm. So this is a verifier. What is that algorithm? This is some algorithm, and it's a saint. That's why it has a halo. What does that mean? The algorithm is not part of the machine learning. The algorithm is something I design, and I know that it's sound in the sense that I will define in a minute, okay? This algorithm, what it's capable of doing is, is the verification algorithm is going to ask questions, and the model now, in addition to just give y, is going to be able to answer the question. So question 1, answer 1, question 2, answer 2. Let's say we go through our rounds of these question and answers, and at the end, the verifier now should decide whether he wants to accept y or reject y. Okay? So accept means I accept y as the correct output of x. Okay, and reject means I don't. It doesn't mean that it's the wrong answer. It means that I do not accept it. And what is it that we demand here? We demand the following. We demand what I call soundness, the soundness of the verifier. And that is that for every single x, remember, we want now worst case guarantees, not 99%. For every single x, I would like v to reject incorrect y's with high probability over the verifier's coins. So the verifier tosses the coins. He knows he's the one who gets to reject. So I don't want him to accept incorrect y's. So what do I say? I say that he will indeed reject them with very high probability. But of course, how do you build such a verifier? It's very easy. The verifier just says reject, 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 reject is very sound. It's all good. It's not good enough. So we want an extra, and we want that H actually is self-provable. What does that mean? I want that the probability over the x's. Now there is a probability over the x's. So there'll be a distribution in a second. X is taken from some distribution, mu, and I want the probability that he will convince the verifier that y is correct is, let's say, bigger than beta. You can think of this as large. So the combination that you always reject incorrect ones, and that you are able to convince with high probability over the distribution means what? It means that you have utility because you are able to reduce y and prove that it's correct, but you never can cheat me. Okay. Now, if we think about it, this is a worst case guarantee, because for every x, this is a distributional guarantee. And that's what these large language models look like. They work 99% of the time. So they will satisfy this if I can manage to take them and make them also prove their answers. But at least I know that I will know when they're wrong. If we compare this to the kind of definition in the literature, without this extra verifier and the soundness guarantee, what do we have? We have interactive proof. So interactive proofs, we usually have something called completeness, which you saw it in the context of the pack verification, where we want really that for every x, the prover can compute y is correct with high probability, maybe even probability 1. Here I'm saying, no, this large language model, it's like a heuristic. It doesn't always compute correct. But I still want to trust it when it does do it correctly. And then if you think about standard machine learning accuracy, again, it's a distributional over x. So these are not the same because I'm relaxing completeness as compared to interactive proofs, but I'm doing much better in terms of soundness compared to standard machine learning accuracy. Okay? All right, so that's a goal. It's a goal to make these large language models not only give us answers, but also give us proofs that the answer is correct. But I am going to, when I say the word proof, I don't mean as in lean or in classical mathematical proof. I allow a probability of error. So there is a probability of error even here in the soundness. So it's high probability, let's say 1 minus exponentially small. And second, I allow interaction because interaction might help me. Maybe just to produce a written proof is going to be too difficult. But I'm allowing this mechanism of back and forth interaction, which has helped since the 80s quite a bit in terms of interactive proof. You know, probably IP equal to P space. All these results show the power of interaction and probabilism. Okay, so if we have a little bit of notation, mu is a distribution, V is this efficient and sound verification algorithm. And what kind of hypothesis models are we going to show results for? They're going to be really like the LLMs that you use. You know, sometimes people say you love and use. I don't know what you love, but you use. Or your children use it, or your grandchildren use it. But in any case, in other words, I'm going to talk about models, and this is where the results are going to lie, which are sequence generators. And we'll say and the model has some parameters, which are these parameters of these large transformers. And precise definition, self-provability, we say that it's beta self-provable with respect to a specific verifier, so we fix the verifier. With respect to it and the distribution, we want the probability that it will be convinced to accept be greater than beta. So the goal is really to learn parameters, okay, of a model that maximize the probability that they can convince me. Not just they come up with an answer, but they can actually convince me. Okay, so how do you do that? So it's kind of, I always thought that, and then in the meeting last week in MSRI and SL Math and Simon's, people kept repeating that. We always think about proofs, or at least I think about it as something that requires sort of deep mathematical thinking, and you understand where the proof is going. You don't just go line by line and somehow it works out, okay? But the proofs here actually are going to be a little bit more like, you know, line by line, and at the end, you're going to get a correct proof. So let me explain that more precisely. So right now, the way these models work are sequence to sequence, meaning sequence comes in, sequence of what? Over some alphabet, which usually these alphabet are not just A, B, C, but they're called tokens, okay? And from a sequence to a sequence, the size might change of these input and output sequences. And furthermore, they're what's called autoregressive. What does that mean? It means that I put the input in, like X, say, and it comes out as first token, then I feed in the X concatenated with that token, comes out another token, and so forth. So if you see this arrow coming back, so it uses X and previously generated outputs to generate the Y. Okay, that's how they work. Okay, how is that helping me to understand how to make these models prove their answers? So in the same way, so these models, so for example, here it says once upon, and then a time, okay? These models don't really just compute the next, in this case, word, but they actually come up, they compute this sort of predictive probability distribution of what the next word is likely to be, and then they output, according to that distribution, the next token, which would have been an A and a time and so forth. So in our case, our goal is to train a model that generates mathematical proofs one token at a time, really very similarly to text generation. And how do we do that? So first of all, we have this new concept, gadget or creature, which we call the transcript generator. So what do we mean that? Suppose you had a box T, and T, you could give it X, and it outputs to you Y and proof. Another X, another Y and proof, okay? So it generates transcripts of interactions between that prover algorithm, the H, and the verifier. Where do you get it from? We'll talk about in a minute, but suppose you could. For example, you could have you have mathematical proofs in your history, in your bank, and you have theorem X answer, could be a proof of X and then a proof that that proof is correct, Or it could be just X is a calculation that you've done, Y is the result of the calculation, and then pi is the back and forth that convinces you that Y was the correct result of the calculation. So we have, in any case, a generator that when I give him a prefix of this transcript, it gives me the next token. And to train, given such a thing, okay, so I think about pi as Q1, first question, answer, second question, answer, and so forth. I want to have a way to learn, and I don't want to just do it ad hoc. I want to have a theorem that shows that it's doable. I want to be able to have an H that doesn't just go from X to Y, but gets to X to Y followed by a transcript, okay? A transcript, which is just interactive things. So suppose I had access to a history, a bank of these kind of things. They go from X to Y followed by pi. Is there a question here? Because just understand what the letters mean. Pi is just the history of communication. Okay. And then we can prove the following theorem, that when it's realizable, so in other words, there is in this family, like the LLM family, parameters exist that will be able to prove to you things, okay? Under some convexity, Lifshitz assumptions, which are standard in machine learning, if you are indeed given an access to this kind of bank of transcript generation, you will be able, and in a verifier, which is sound, and a distribution, and a model that went just from X to Y, you will be able to actually extend it to a model that proves that Y was correct. How? You use essentially gradient descent, but and one could go into it, but we don't really have time. But the point is really that this is a standard algorithm, because in a sense, what you have here, you have a lot of text, and you're trying to come up with the parameters that will enable you to match a text. When you predict the text, it will match an accepting transcript, a transcript that would convince the verifier to accept. What's interesting about this is how many iterations of gradient descent you have to do. And the number of iterations, this is sort of standard stuff, but here this constant is interesting because this corresponds to the length of the prover's messages. Remember, like the verifier asked a question, there was an answer, question, answer. The lengthier the conversation, the more time it will take to come up with good proofs, which is consistent with these LLMs that the longer sequences are, the more error comes in. Because every time that you output another token to extend the sequence, you might make an error. Okay, so that's the, that's the theorem, the convergent theorem. No, I'm always going backwards here. The big question that you should ask is, where am I getting these transcript generators? So actually, we have from the interactive proof theory a creature called doubly efficient proofs for lots of computations, which means that for previous x, not the new x that you want, because otherwise, what's the point? You have ways to actually play with a real prover and that generates y and gives you interactive proofs. And those could be the bank on which you train for future x's. There are other ways to come up with this, but this is sort of the most sound one. And then the algorithm, as I said, you've got these sequences, you optimize toward accepting transcripts, you gradient descent. So first step, you collect accepting transcripts. Second step, you do this, compute these logits, and then you optimize the best data that will do an agreement with accepted transcripts. Too much detail. Okay, there's also another version, which is a sort of reinforcement learning verifier feedback. So we have a verifier after all. And when I give him answers, he could say, no, this is not even a prefix of something that will convince me. So if you do this carefully, you could just by looking at these rejections come up with transcripts. And at the end, I'm a theoretician, but my students also, all specifically, knows also how to build these things. So we've tried this on the sort of the simplest algorithm. So everybody here who is trained as a computer scientist, the first algorithm you learn is Euclid's algorithm for computing greatest common divisor. So you get two numbers, gives you the greatest common divisor. How do you check that it's correct? Seems really easy, right? You just divide and see that the claim, the greatest divisor, divide, but how do you know it's the greatest one? So this we know already is a simple observation, and that is that if you can also get the Bezout coefficients, okay, so the coefficients such a linear, say you want x1 and x2 GCD of them, the Bezout coefficients are z1, z2, such that the linear combination z1, x1 plus z2, x2 is equal to GCD. Okay, so if you can check, indeed, this line here helps, holds, if the combination divides both x1 and x2, n is equal to the claimed GCD, it is the greatest common divisor. It's an easy thing to verify. So that means that these Z1, Z2, they're a proof. If you had them, you could just do the linear combination, check that it's equal to this proclaimed greatest common divisor. So for this example, what you'd like is to take a model that you give him x1, x2, and you just output D, and then say, you know what, now I'd like also to have the Bezout coefficients. But the model didn't necessarily run Euclid's algorithm that computes these Bezout coefficients as we went along. Who knows how that algorithm worked? But what we can do by running our algorithm from the theorem, in fact, make this model output also the Bezout coefficients. So essentially, not only just give you the answer, which is 2 here, but sorry, the answer, well, never mind. These are the empirical results, and that is, there's a model that can do GCD correctly 99.8% of the time. If we also want a proof, so we want to be able to verify, essentially there are 2 methods we've used at the end getting to 96%. So you say, but it's better to have 99%. I agree, but I'd like to have my calculations also verified as correct. So in some world, you can think that adding this machinery of verifying can even get you models that are more correct than the 99%. And I don't know if those who have been following, there's this DeepSeek and so forth. Apparently, a lot of the magic sauce there is that they verify intermediate results, and that enables them to know where to dedicate their effort. Okay. I said that this is related to a lot of things in mathematics, Lean, MetaMath, Coq. There's work that people have been doing about having automatic verification of theorems. And so these theorems could be, and they're proofs generated by large language models. What we are adding to the game here is probabilism of error, rounds of interaction, and it's a general model that actually, these are special cases of it. What else do I want to say? It's a very fast-moving field, obviously. So this is actually a slide that was I took a screenshot from the workshop last week, and they're sort of pointing out how this is what could be proved in 2019, and this is 2024. We've got all these models doing much more fancy mathematics. This is not meaning that they're replacing mathematicians in any way. These are all, type of theorems that people could prove. It's just that also the algorithms can prove and verify. I want to say that there was a lot of TOC, classical theory of computing inspiration here, because as you saw, interactive proofs came into play. There's also something called program checking, which is very relevant to this research. There are differences between these concepts, which are summarized on the slide, but since we're almost out of time, it's only an hour, right? I just want to say that there's a lot of future directions here. So this was an explicit verifier for a task. You really would like a universal verifier. You'd like every task to have like a way to come up with a verifier and then a prover. And we have some work in this direction. It would be interesting to know whether you need those Lifshitz conditions, or is there some combinatorial dimension of the problem or the proof system that tells you whether you will be able to get proofs or not get proofs. And tomorrow, I guess I will speak about the third one, which is robustness and resilience. So thank you. Questions? Any more questions? Yeah.
In interactive proofs, MIP, multiplayer interactive proofs are much more powerful. So, and one thing you can do with models easily is spawn more copies and maybe guarantee or ask that they not talk to each other. Do you get a lot of mileage out of it? Is it possible to?
You might. So, I mean, at this point, you could take that. You could do a PCP concept, right? Where they produce something where you only have to poke a few points. The multiple interactive proofs is kind of attractive because there are multiple LLMs out there. Okay, they even compete with each other. They're not even made by the same company. But in this case, in some sense, the provers in multiple interactive proofs, they have a joint strategy. It's just that we're assuming they don't talk to each other. So if you think about these models as benign, then it's okay. So 2 copies of ChatGPT, somehow one is somewhere far away and they cannot discuss, or you believe they don't discuss. Certainly internally, if they wanted to check the correctness of their algorithms, they could do that. Just take 2 copies, do this type of, try to convince a verifier, and this would be a way to check the soundness of their system. But if you think about me as the client, how do I trust that these don't collaborate? That's the only question. But obviously, they will have more power. There will be more succinct. We know that we have more succinct proofs, for one thing. And if you think about this gradient descent thing, the succinctness of the proof is makes a big difference for how many iterations of the gradient descent you have to do.
Yes. I have a question maybe about how adversarial I should think the distribution over data as being. And like standard pack learning, it's a distribution-free notion, whereas it seemed like in the self-proving model, you'd fix the distribution view. Is it too much to hope for that you would get self-proving for all distributions over data for reasonable classes, or is this somehow in your Lipschitzness assumption, or?
So by adversarial, you're saying you would like it to be for, any mu.
Right. We could get it, but it seems maybe it's too strong.
But we don't even have accuracy for any mu. So even for GCD, so there's this work by Charton, and he figured out a particular log distribution, some distribution on which is the accuracy of 99%. So my thinking is once we get over that barrier, you could, my guess is you could also get the provability. So for example, a reduction of that sort is if you have the ability to get correctness, then you have the ability to doing provability. That's something that I could see that happening, but these are tied. What?
I think this is not true in the pack setting, but maybe in.
In the pack setting, they don't, you mean in pack verification?
Okay, maybe I'll ask offline.
I'm separating the learning and the verification.
Yeah, it seems related to like this reliable and probably useful learning. Seems like you could, okay, ask offline, sorry.
I don't think any of this is worst case, I guarantee on for X. But maybe we can talk about it afterwards.
Okay, if there are no further questions, let's thank Shafi again.
Thank you.